Recording. There we go. I am recording. Hi. Any questions from last time? Where did we end up? What was the last thing we talked about?
We talked about, you had the question for us on like what are the three relationships of, it was density, temperature, and pressure.
Ah, okay. And what did you guys write about that? Do you have any questions about stuff we did last time? I mean,
I have a question.
Okay, Lena.
On the chapter 2 worksheet, it said on 15, it said draw an example of a 500 HPA station plot. Do you want us to like, I don't know, that one was confusing to me.
Okay, first of all, let's do this. I'm going to share my screen. Over here. This is the one thing about Zoom I hate. I want my windows to be maximized at all times. There we go. I'm going to put on glasses and a blackboard. You see the blackboard?
Yes.
Okay, first of all, we say that the unit of pressure is a millibar. What's standard sea level pressure? Did I go through that with? I did go through that with you, didn't I?
Mm-hmm.
What's called MSLP?
1013.25
millibars, right? That's standard mean sea level pressure. That's what that means. So our standard sea level pressure. Okay, so a millibar is what I use. That's the same thing as this thing called a hectopascal, HPA. We're going to do another math lab. We'll do the math lab part 2 coming up, not right away, but eventually. And HPA, hecto is a prefix, and Pascal is actually what we call this, 100 pascals. That's the unit of pressure. For you guys in my class, I don't care about this. Focus on millibars, okay? So 500 millibars, the idea is this. So I'm gonna do this. If I look on our webpage, which I can, oh, look at that, it's snowing out. Have you seen outside lately? It's awful. If I go here to analysis data, I can do an upper level map, and I can do one at 500 millibars. What am I doing? I'm just going to do this one. 500 millibars. And I get these station obs that look like this. Okay. Now, in the book, they also talk about the surface plot. Is the surface plot in this chapter? Did you guys do the surface plot? Like if I give you this,
yeah, it's in that chapter.
Yeah,
it's in that chapter. Okay, so we're going to go through this in class too. So if you don't get everything right the first time, we'll do this. At 500 millibars, we do the same thing, except the difference is we put the temperature, the dew point, and we put this number here, and this number to the upper right is how high up do you have to go to reach 500 millibars. So you could use in a book example, you could just look at a 500 millibar plot, like Google search that even and just use one of those.
I'm sorry, what's that circled number again?
That's how high above the earth, actually it's how high above sea level, you have to go to get 500 millibars. So think about this, right? You're on the ground. What's our working definition of air pressure is what?
The weight of the air above us.
So when you're on the bottom, you're about, all of the atmosphere is about 1,000 millibars, 1,013.25 on average at sea level, but around 1,000 millibars. So I'm going up through half of the mass of the atmosphere to get to 500 millibars. And I'm saying, how high up do I have to go above sea level to reach 500 millibars? And this number here, 545, you'd put a 0 at the end of it. So you're going up 5,450 meters or 5.45 kilometers. That's how high.
So then the circle number would be 5,370.
Yeah. Yep. You just throw the 0 on the end of that for the 500.
Okay, that makes sense.
Okay. Anyway, So that's what you're doing, Lena. Does that answer your question?
Yeah, thank you.
Other questions?
Okay, yeah, about that that map. Why don't they have the cloud cover?
Because you don't care. Because you're not measuring cloud cover. You're only looking at cloud cover is an observation you have from the ground.
Oh, that's right. That's right.
You're up there, you don't have cloud cover. Now you
Right.
could shade it in if the dew point's less than 5. That's just standard practice, but dew point depression.
All right, and can we take a look at the cold snap?
Yeah, really? You want to talk about weather? Why would you
Of
want to talk?
course.
It's not nearly as bad.
It's
But I
still
mean, it's
brutal.
bad. It's just not really as bad.
Still going to be brutal.
Here's the problem is that the temperatures, the GFS is about 10 degrees too cold. So we do have definitely cold air coming in this weekend. It stays in place for a long period of time.
Oh, that's not as bad as it
You
used
see
to
this
be.
green on here? That's negative 20s. That's just a lot of cold air for a long time. We really don't get out of the real cold air till, I don't know, then, if this is even right, we're only talking about the 30s. So we're not going to see highs in the 40s probably for the next couple of weeks at least.
I don't even trust it that far out.
But we're not even really getting to the point where we're looking at spring. We are definitely looking at a cold pattern for the next few weeks at least. So if you like frigid cold, it's bad. If you like snow, it's bad. Look at the snow right now. It's actually coming down pretty hard. You see that?
Oh, it's not as bad here. Oh, wait, yes, it is. Never mind.
So it's a pretty good snowfall happening, and we're looking at about 2 to 4 inches. Is what I'm thinking.
Is there a way to view wind chill?
If I go here, I can show you wind chill.
Using the GFS? I know there is on Pivotal Weather, but I
We
don't
don't
know.
plot that out.
Okay.
You look at it here. It's gonna be cold. It'll be in the double digits below freezing or
This'll
below
be-
0.
This will be similar to a couple years ago.
It's not the super cold. It's not like the polar vortex. You may remember that. Okay,
Yeah, I remember
so
that.
what's the relationship between those two? Nick, we'll start with you, buddy.
I don't know.
Can't say I don't know. You know, here's the thing. If you get the wrong answer, I know you don't know.
I actually don't even have a guess at it though, honestly.
Talk it through. Everybody give it up to Nick, right? Encouragement, scream a little bit, maybe some hands up, party stickers. Talk to the class, Nick, and everybody help him out.
I don't know.
What do you see?
Well, I'm pretty sure you're saying the relationship between like that P and that P.
Okay, stop. What's this?
Is that rho? Or no, is that not rho? Okay, I don't know what that is.
Okay, where do you have it in your notes, Nick?
I was hoping I did.
Okay, you
But
see
I actually don't think I did.
that. Avi, explain these 2 letters.
One's density and the other is pressure.
Which one's what?
I have it in my notes. Wait, I don't want to be wrong, but the density is the one on the right, so in the middle.
What Greek letter is that?
I always forget. I don't remember what Greek letter it was, but
Type of boat, Avi. You
I'm
do it
sorry?
3 times. What do you do to a boat 3 times?
row.
Oh yeah, so one of them was wrong. Yeah.
And what's this?
Pressure.
Okay. So we're going back to Nick.
Okay. So what's the relationship between row and pressure?
Well, what's rho? You wouldn't say rho. You'd say what?
You would say I don't know. I don't know.
Well, what does rho stand for?
Density.
Oh, okay, density.
Everybody take off your mic, or you're muting. Put your mic on, and I want the conversation. Everybody's talking out loud. What is this letter? What's the Greek letter called? Everybody?
Rho.
Row.
What's this stand for?
Density.
Pressure.
What's this letter?
P.
Stands for what?
Pressure.
I want the relationship between those two things. So what's first?
Pressure. Wait.
Is it, as
Julia,
the
go ahead.
pressure goes up, the density goes down? Is that the relationship?
Why do you think that? What do you see? What's the first thing you need to do, first of all?
Make a constant. Right? Like have
Zach, was that
T-
you?
Yeah, like make T the constant.
So what does that mean to make it constant?
To not let it change. Like keep it a static number or a static position.
So what does that mean you have to do with your brain?
Make the box like put it into context of the box.
Correct. Put it in context of the box. Yes. Julia? So what do you see?
I guess like when you look at it in the box, like we did before, like when the box gets bigger and then there's, or when it gets, wait.
What do you have to do first, Julia?
I don't know.
Tom?
Increase the pressure.
I explain.
Well, if you keep the temperature constant and increase
What does that
the
look like?
pressure in reference to the box,
Yes.
it would it would probably get smaller. The box would get smaller.
Thank you for doing that correction. You guys are not doing what I need you to do. You need to explain what is happening in your mind in the box, or like Zach said, in the context of the box. You have to explain what you are seeing. So far, I haven't seen anyone explain to me what has to happen first. What did I say has to happen first?
Pressure drops.
No, that's not what happened first. In dealing with the relationship between these two guys, what happens first? Guys, listen to me. To get the relationship between those two, what happens first? What do you have to do first?
Make sure A is constant.
Don't you have to keep one of them constant? The first thing you do is you go, A is constant. Remember we did the number? We did like 8 equals 4 over 2. We said, oh, if I make, I'll keep this the same and I'll make this 6. Or that's silly, 8 over 2. I'll make this 6, and what is, you have to change the numbers first after you hold the first one constant. So if I'm asking you, what do you do with the relationship between those two, what's the first thing that you have to do?
Make sure temperature is constant.
Isn't that what we said? I mean, we've said that. We have to make sure this is constant. Then I asked, well, in the context of the box, what does that look like to you? Lena,
like if the temperature's constant, then like in the box, wouldn't the molecules like be moving at a constant rate because there's no heating or cooling being added?
okay, I'm not happy with saying
Yeah.
heating and cooling being added. But they're
Oh, there's
moving it.
no.
So show me that. Show it to me. Everybody. I'm waiting. Guys, show me the molecules moving. Show it to me. So no matter what happens, they can't go faster than this. Then what do you have to do? After you hold this constant, what's next?
Change one of the variables or change pressure or density.
Okay, change one of the variables. Now, Zach, for the sake of trying to figure out what's the easiest way to think about it, which one do you want to change first?
Would density be easier? So you just add more molecules or remove more molecules? It's like the mass.
Oh, okay, fine. Did you hear what he said? Ian, what did he say? Repeat what he said.
Do the density, change the density, add or take out, like add more molecules or remove
Okay,
molecules.
so if I put more molecules in this box, keeping them all moving the same way, what will that do to the density? Everybody, hand signal. What will that do to the density?
Freeze.
Everybody, right? See, this is what's so hard. I know this is difficult for you because you have to learn how to be a person of thought. So you have to think this through. Are you thinking it through? The density goes up if you put more molecules in there. Does that make sense? Yes or no? Because if you say no, that's okay too. You just have to say it doesn't make sense.
It makes sense.
Everybody, does it make sense?
Yes.
Yeah.
Okay. So as it got more dense and they're all moving at the same rate, what will that do to the pressure on the box?
Increase pressure.
Won't there be more molecules hitting the walls? Won't that make the pressure go up?
Yep.
Okay, so by that thought experiment alone, you now said that the density goes up, the pressure goes up if the temperature stays constant. Is that what you said?
Yes.
Okay, now try something else. Try changing the density in a different way instead of putting more molecules in it. Sam.
Ask that again.
Change the density in a different way, other than putting more molecules in it.
Oh, you could drop the pressure.
No, then you're changing the pressure. Unless you change the density.
Well, if the pressure drops, the density drops as well, right?
Listen to what I'm saying. You're telling, okay, Zach told me, let's change the density first. You could have changed the pressure first, but we said, let's change the density first. In other words, the density becomes the independent variable. Who controls the independent variable?
We do.
You do. The dependent variable will change because of it. If I said change the density and you say by changing the pressure, then you're backwards. Change the density first. First thing Zach said, put more molecules in the box. Is there another way to change the density?
Yes.
Shannon, what do you say?
Could you increase the temperature?
No, because what did I say you have to do first?
Or would you increase the pressure?
No,
No, wait, I have.
you can't change the other ones if I'm saying change the density. I'm just saying in your head, could you make this box, look, could you make it more dense without putting in more molecules?
Yes.
Yes.
How?
Change the size of the box.
Okay, change the
Increase
size of the
mass.
box. So I can have, see the molecules in the box? You see it? Make the box smaller.
More dense.
It's more dense, okay. And if it's more dense, what happens to pressure? In that scenario, they're all still moving the same speed.
Pressure would go up.
Why is that?
Less square space equals more pressure due to the density.
Okay, there's less,
Area.
there's less, what kind of area? You said, so Shannon, you said square space, which I get it, right? And you said area, Sam, so put them together and you get, there's less square area, which is really the basically the surface area, right? There's less surface area of the box. Do you see that though? You've changed the density, made it more dense, and now the pressure goes up. So by thinking through it, you've determined the relationship between the two, assuming temperature is constant. If you use your brain to visualize it, you can do this. Because you're understanding the concept. Now, what if I said, instead of changing the density first, change the pressure first? Inside the box, what can you imagine the pressure, how could you make the pressure more inside the box?
Um,
Go ahead, Shannon. What do you think?
more density or temperature?
But I'm saying, all I want you to do is you control seeing inside the box, the molecules are exerting more pressure on the inside walls. How can you visualize that occurring? Ian, what about it?
I don't really know for pressure. I mean, could you possibly, if you like took out molecules as you made the box smaller, would it also increase pressure? But I don't know if that would, since densities.
Do you agree that this is, and so Ian is kind of interesting. He's like, I don't really know how to do this. And that's kind of the answer, because the only way that you could really do that is what's the force is how fast the molecules are hitting the wall of the box. And since you can't change that, you can't change the force. So you'd have to make the walls smaller, but making the walls smaller is changing the volume. So I guess you could do it that way, right? You could just say, well, if I picture a smaller wall, there'll be more pressure, right? If I were to take a big block of wood and hit it with another block of wood, would I do much damage to the bottom block of wood? Probably not. What if I took a hammer, hit it the same strength? Would that dent the wood? Yeah, because I have the same force over a smaller area, increases the pressure. If I make the area really small, like hitting a nail, then it goes right through the wood, right? Have you ever seen movies from the 1950s, the bad sci-fi movies? There's always a woman who wears extremely high heels, and the first thing they have to do is take off their shoes, right? Because if you ran across ground in high heels, what would you do?
You'd trip.
Well, you trip because you have high heels. It's awkward. But what else would you do? You ever try to? Anybody wear high heels and walk on ground? on the Earth, what do?
The heels sink in.
You just go right into the ground. That would be a bad way to run. So he's got to take off the shoes. Okay. So that's the first one. All right. Now you guys use your brain the same way. Tell me the relationship between this and this.
So yeah, we have to keep density the same. and
So
keep
the first thing you have to
density
do is
constant.
keep density same. So what do you see, Zach?
I see it's the same like amount of like particles like in the box per volume, right?
And do you agree that what are the two things you can't change then?
Mass and volume. You
Okay.
can't change those two.
So you have a box, you have the same number of molecules. You're not changing that. Then you change one of them. Which is the easiest one to change?
Temperature.
The temperature.
Temperature. He's going temperature, right? So what do you see?
So, would it be like more kinetic energy so the molecules are moving faster?
So really, yeah, you're exactly right, Zach. But all you really need to see is that the molecules move faster. And if they're moving faster, how are they going to hit the walls?
They're going to hit the walls with more force, which will increase pressure too.
Right? They're going to hit the wall with more force. What's a better way to say that? They're going to hit the wall with more what?
Momentum.
Oh,
Who said that? Good. More momentum. You're going to hit the ground with more, or hit the walls with more momentum. And it's change in the momentum that gives the force. But whatever, they hit with more force. So if temperature goes up, what does pressure do?
Increases.
It goes up and temperature goes up if density is the same. So we have pressure is directly proportional.
I have a question about that last one.
Okay, yeah, who said that?
That was me, Nick.
Okay, Nick, go ahead.
Why does density stay the same on that one, but when the pressure went up on the last example, it went up?
Remember, you're dealing with relationships between two variables, right? Which means you have three variables in that whole thing. This whole thing is you have three variables dealing with it. So the first thing you have to do is you have to hold one of them constant. So you need to say in your brain, what does that variable mean? What does it look like when it is constant? So the first thing you say, if I want the relationship between pressure and temperature, the first thing I need to do is hold the density the same. So that looks like I just have a box with molecules. I don't add molecules. I don't change the size of the box. I'm holding that way. That's what I mean by holding something constant. And then you change the other ones. So when you start looking at this, you have pressure is directly proportional to temperature if density is constant. That's what this is. Now, what's the last one? The last one is what's the relationship between density and temperature if pressure is constant? Notice I'm using colors to look. I have green, blue, and red to look at the relationships. And really, I guess I should have said this, right? Just to keep the colors all the same.
Are these going to be inversely proportionate?
Well, okay, Tim, why do you think that? You want to kind of explain through your reasoning to them.
Because it's kind of hard to put into words, I guess. But if you increase temperature,
What's the first thing you have to hold constant?
well, yeah, you're going to hold pressure constant.
Which means you can't do what?
A lot of things. You can't change the size of the box. You can't increase temperature.
Well, you could change the size of the box.
Oh yeah, yeah, but you'd have to also decrease the temperature.
Oh, why is that?
Because as you decrease,
You said that like if you knew what you were talking about.
I do know what I'm talking.
So explain that to somebody who doesn't know what you're talking about.
So when you want to keep pressure constant and you decrease the size of the box with the same molecules moving at the same temperature, it's going to increase the pressure because the density increases, and the density and the pressure are directly proportionate to each other. So when you decrease the size of the box, you need to decrease the pressure as well, so that the molecules in the higher dense area aren't hitting as fast, or as hard, I should say.
Ryan, what do you think? Did you follow that?
Sort of.
Okay. So listen, Ryan, the answer to my question, did you follow that, is no.
No.
You didn't follow that. You may have gotten a few things, but you got lost and you didn't follow it. I mean, am I right? Is that true of most of you? I know this stuff better than all of you put together, right? And I was struggling through, and there was a couple of times he made comments that were wrong because he fell off his bike. You know what I'm saying? He fell off his bike. So, Tim, try it again. Get better at it. And then this time, rather than just explaining it to everyone, explain it to Ryan. And then Ryan, your job is to stop him every time you like, I don't really know what you, wait, what'd you say?
Okay. So Ryan, in this situation, we have to keep pressure constant to find the relationship between density and temperature.
Yeah.
And so in order to find that relationship, we kind of have to move things around, change a variable. And when you change variables, you have to make sure that whatever is staying constant remains constant. So let's say we want to change the density. So we talked earlier, to change density, you can either shrink or expand the box.
Okay, so do one of, so first of all, Tim, that was way more better teaching. It was way better. It was clear, right, Ryan? I mean, so
yeah.
So let's go for the first one, make the box, choose one, make the box.
Okay, we're gonna make the box smaller here. So when we make the box smaller, you can imagine that all the particles in the normal box are confined to a smaller area.
A smaller volume.
Yeah, smaller volume. And the way they were moving before, they're moving the same way because we haven't done anything with temperature. So they're still, moving at the same speed and everything. But in a smaller volume, they're going to be hitting the walls a lot more often because there's less distance between the sides of the box. And what we said before, pressure increases when you're, hitting the walls of the box at a higher rate, kind of. And we can't have this because the pressure, we have to keep the pressure constant. Have I lost you yet?
No, I think I got it. So you would have to decrease the temperature so that they aren't hitting the walls as fast and the pressure.
That's what I was getting to.
Staying the same.
And dude, right there, Tim, and everybody really, is now you're starting to see what learning looks like. Because Tim was explaining things really well. And did you see that he struggled a little bit because he knew what he wanted to, what he was thinking. He just had a hard time figuring out what to say. So he had to work it through. And then luckily, he did a good job to that point because what did Ryan do? He's like, oh yeah, I understand what you're saying. So you're gonna have to slow the temperature down. Because you don't want to hit the walls as hard. So you slow the molecules down, which is cooler. That's what learning looks like. When's the last time you did, God, did you do that in high school a lot? Or did you just sit there and listen to the teacher, blah, 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 and you write notes? This is learning. And Tim, do you agree that the second time you went through, you were better? You still start you were catching things that you were saying, no, that's probably not really good, right?
Yeah.
You had to struggle through it. You probably, if you did it this third or fourth time, you'd probably go, I got it.
Yeah, I don't want to though.
Right. And Tim and Ryan, you would be like, you started to get it and now that I would say, all right, Ryan, you explain it. You actually did. Yeah. So you see the molecules would move slower. Now, that doesn't mean that everybody here has that ability at this point, right? Because you haven't been doing it. So what I'm going to do is I'm going to put you into breakout rooms and I'm going to give you a chance to explain that and then write down the final relationship here as well. Okay, so those three variables, I want you to explain that. And what I'd like to do is take the best person, like say, who understands this the best? You say it. And then take the person who may understands this the least, say, well, wait, let me see if I get that. So you become the person being taught. Then after that, you switch roles. Okay? So I'm going to stop with this. I'm going to give you about 5 minutes to do this. Oops, shoot, hold on. It's the thing about this Blackboard. I want you to try it out loud.
Much force hitting the sides.
Yeah. Oh, yeah, yeah, yeah. That makes sense. So, yeah. Yeah, I accidentally said that increased density and also increased temperature to keep pressure the same, then I realized that was completely wrong.
That's okay.
It's okay.
So, yeah, do you guys understand this?
I'll be honest, I think I'm a little bit lost. So
Well, then you say it.
wait, hold on. I just need clarification on something. So are we explaining how pressure and density go up and temperature stays constant, or just that whole equation in general?
So right now we're explaining, so we have like the three variables of pressure, density, and temperature. And so right now we're keeping pressure constant, so we can't change the force of the molecules hitting the walls of the box or the surface area of the box. Am I correct with that one?
Well, you could, Zach, right? If you changed the force and made the area
Oh, so
bigger, wouldn't the pressure stay the same?
they would yeah, so
Because that's the idea of A equals B over C. B and C both get bigger and A doesn't change.
yeah,
So
yeah,
the
that
pressure
makes-
can not change if the force and the area get larger.
Okay, so as long as we keep that directly proportional relationship between the force and the area of the pressure, so pressure won't change, and so that will keep. So it's like doing an equation within an equation, right? So to break it down like more simply, force and area is constant, and then
Increases. Wow, this is so hard.
We say like if you increase the temperature, that's going to make the pressure and density go up because molecules are moving faster. So you can't have a small box with that. So the box has to be bigger in order for the molecules not to go crazy and increase the pressure density.
Okay, let's see what you're saying.
Of course it's hard. But
It's so hard to explain things.
once you do it, then everything
Yeah,
else is easy.
exactly.
Yeah, I get how they're like inversely and like directly related because if one thing changes, two other things can change and vice versa. So
Right, you want to make sure one is constant. That's the key thing. So it's always either directly or inversely proportional, but use that word too.
Mm-hmm.
Okay. How's it going, guys? How you doing, Aaron?
Good.
Good.
She just has something in her eye.
Oh, okay. How are you guys explaining it out loud?
I actually feel like we were kind of doing good.
Oh. Bobby, you said a question or something?
What I came to the conclusion of, or what we came to the conclusion of, was that pressure is inversely proportional to temperature if density is constant.
Well, if you made it warmer at the same volume, wouldn't it increase the pressure?
Yes.
So they're directly proportional. If one goes up, the other goes up also.
Okay. Pressure is indirectly.
But then wouldn't the density change if that happened?
Not if you just say it's a box, don't change the volume, don't change the molecules in it. They just move faster. They're going to hit the walls.
Oh. Okay. All right. Yeah, that makes sense.
Okay, we'll be right back.
And then
How's my room of two? How you guys doing?
oh, are we the only room of two?
Yeah, you're the only room of two.
Oh, okay. We're doing pretty good. We were just like looking for the videos. Where do you post your videos?
climate.cod.edu/classes.
Gotcha. Is
Well,
that
that would
like
explain why we couldn't find it on the blackboard.
yeah?
Yeah, right. You won't find it on Blackboard. It's not on Blackboard.
Okay, all right.
There's a lot of videos and Blackboard doesn't let me have that many.
Yeah, but I mean, we feel pretty good about it.
Okay, let me do this then. Close all rooms. So what's the relationship between temperature and density?
Temperature is inversely related to density. Pressure is constant.
It's inversely proportional if pressure is constant. Mhm. These three things are related. Now listen to me. When I take a box of air, and I lift it, what's the first thing that happens to it?
Pressure outside the box decreases.
And what does the pressure inside have to do?
Decreases.
Because the pressure inside and outside are
Same.
Equal.
always the same, right? They're the same, they're equal. When are they the equal? When are they? Answer, always.
Always.
So the pressure goes down inside the box. And how does the pressure go down in the box? By the box doing what?
Expanding.
It's expanding. So do you agree the volume's getting bigger and the density's getting less? But what's the temperature doing? Isn't it getting colder by 10 degrees Celsius per kilometer? So in other words, in that example, what are all three of these things doing? They're all going down when I lift a box of air. That's why these don't work, because the third one is not constant. All three things are changing. Now, all of this can be summarized in the following equation. P equals rho times R times T. This guy is a constant. It's a scientific constant. And the way that I want you to think about it, it just makes things work. You determine what that is based on experiment. It makes it work. Anybody know what this is called? This equation? Aaron, do you know what this equation is?
The ideal gas law.
Ideal gas law.
And that's the third thing every student, if I were king, every student coming out of high school would know. Did you guys study that? Did you study this in high school? Really, Tom? You never had the ideal gas law? Wow. See, to me, that's unacceptable. Ideal gas law, first law of thermodynamics, Newton's second law. Those are the three foundational principles of science. So important that you understand those three laws. Oh, shut up, Siri. Okay, now the way I like to look at this.
Wait, what is R?
It's a constant. It's something that makes it work. Like if you took the density in like kilograms per meter cubed times the temperature, that's not going to get you the pressure. You have to multiply it by something to make it work. And it's always the same number. It would make it work. So what I want you to think about for this ideal gas law is think of this as a teeter-totter. Okay, so here's a teeter-totter. And I'm just going to put equals R on the bottom so that you understand this is in there. And on the left side of the teeter-totter is pressure. That's the left-hand side of the equation. And on the right-hand side of the teeter-totter is density and temperature. So I want you to imagine that there's three kids playing on the playground on this teeter-totter. Pressure is bigger than the two of them, and the other two are on this side. Now, one day, temperature goes, I'm going to eat 100 Twinkies. In order to make this teeter-totter stay balanced, what would pressure have to eat? Pressure would have to eat 100 Twinkies if density just sits there and watches them. Pressure and temperature are directly proportional if the density is constant. Now, the next day, density goes, that looked fun. I think I'm going to eat 100 Twinkies. Temperature goes, no way. I'm not eating any today. In order to maintain the balance, what does pressure have to eat? 100 Twinkies. Pressure and density are directly proportional if temperature is constant. The next day, temperature goes, yeah, I'm going to eat another 100 Twinkies today. Pressure goes, there's no way in hell. 2 days in a row, I ate 100 Twinkies. I'm not eating a Twinkie today. So it refuses to eat any. To maintain the balance, what has to happen?
Pressure has to go up.
Pressure's not going to eat Twinkies.
I mean, density, sorry.
Has to do what? Can't go up.
Oh, decrease, sorry.
It has to throw up 100 Twinkies worth. It's vomiting up Twinkies. That's the ideal gas law. And that will allow me, this is the one equation that you can allow me to understand stuff. Now, you could have written it this way. You could have said RT equals P over rho. And you could say A, B, C. You could. But this is the form that you'll generally see the ideal gas law in. And it's the relationship between pressure, density, and temperature. Now, when I lift a box of air, what's happening to all three of these variables? They're all throwing up Twinkies at a different rate, but there's still the balance is made. So think of an equation, anything with an equal sign is that the left side is the same as the right side. And that's how this thing works. You better know the ideal gas law. You better know the first law of thermodynamics. You better know Newton's second law. And in my world, if I was king, I would suggest that all high school kids learn this, really to a point. You would become smarter people scientifically with that stuff. Does that make sense to you guys? Do you have any questions about this? Now, a couple of you, when you were doing it, was still hard. And Lena, you said, this is hard. And I'm like, well, of course it's hard. Hard things usually do what? What do they require?
Effort.
Okay. In this case, it's practice. You already know what it's supposed to be. You just have to practice speaking. And it is and it's true, even of my students, most people don't get to level 3. They just sit there and they go, I know it well enough. And then I give F's and G's in classes. There's no reason to it. You all have the ability to do it. You just don't have the motivation or the intrinsic drive to figure this out to the point where you're like, damn, I know what this is. And the more people know something, the more they start to realize, well, what does that mean for this? And does this change? And blah, blah, blah. But this is how we deal with stuff. Okay? Any questions on this? All right. Switching gears for a second. So I lift the box of air and oops, let me do this. I lift the box of air and pressure's going to go down, the box is going to expand, and the temperature is going to cool. What rate does the temperature cool at? What's the number?
Like 6.5 degrees Celsius.
No, that's the environment.
Is it negative 10?
10 what?
Degrees Celsius?
More than that. 10 degrees Celsius.
Per kilometer.
Per kilometer.
Right? Rate of cooling. What is that called?
The dry adiabatic lapse rate.
That's the dry adiabatic lapse rate. What's this Greek letter? Nick, what's that Greek letter?
I don't know. I do not know what that letter is. I'm sorry.
Okay, so Nick, what you need to do is you need to write down all the symbols and go, what does that mean? You should put this in a place in your notes that's clear and easy to access until you got it.
I have that written down already.
What does it say? But I mean, put them all in one place so that everything is in one place.
What do you mean? Everything's in one place?
Well, like have a cheat sheet, like a flashcard, all the symbols and all the answers.
Yeah, probably ready to do that.
Yeah. Okay. Listen to what you said. You said, I should do that. I didn't tell you you should. You said you should. You're right. What Greek letter is this?
It is
On the count of three, everybody. 1, 2, 3.
Gamma.
Gamma. What does it stand for? On the count of 3. 1, 2, 3.
Lapse rate.
Lapse rate.
Lapse rate.
What's the lapse rate? On the count of 3. 1, 2, 3.
Rate of cooling.
Decrease.
Rate of cooling.
Rate of cooling.
Right? By the way, notice this stuff is not, you're not really learning, you're memorizing. You know the easiest way to memorize something? Just do it.
Repetition.
Repetition. That's all it is. It's repetition. And in class, I've said this 1,000 times. What's that letter? And I'll have somebody answer it. The rest of you won't. You know what I find amazing? I'm just going to go off on a tangent here just for a second. You know what? And I've never gotten this. Where'd you guys go? Oh. I have never understood this. Do you guys listen to me? I assume you listen to music. Do you guys know the words of songs? Like, I still have to look at a cheat sheet for singing Happy Birthday. I'm like, I always forget the second line. And there's some people like, well, this is the song, and here's when they start singing it. I'm a musician. Anybody a musician? Anybody here into music? So I'm a musician. I mean, all I do is I know what the bass player is doing. I know what the drum beat is. I know what the keyboards are doing. I know the guitar, right? I know musically, but sometimes I'm like, I don't even know. Are they saying words? I don't even know what they're saying. And there's these people, and they're like, oh, and they're singing along with it. Lena, why do you sing along with the song? How do you know those words?
Because I listened to the song, I guess, so many times, so that would be repetition.
Okay, so in other words, gamma, lapse rate, rate of cooling, that's not a learning thing. Do you agree that the ideal gas law and how it works and think that's learning? Sometimes you just have to do that. So when I ask you to unmic and then say the response, there's a reason for that. The things that you have to learn by repetition, I'm giving the option to repeat. I don't think that's the right word, is it? All right. So Tim has said 6.5 degrees. I said the dry adiabatic lapse rate is 10 degrees Celsius per kilometer. Tim's original thing was 6.5 degrees Celsius per kilometer. What is that?
That's the average lapse rate in the troposphere. Or something.
Okay, so the troposphere. So that's the average lapse rate of the troposphere. Now, I'm glad that you remembered that number. Did the rest of you know that number? So imagine this, guys. Imagine that I lift this parcel and I'm going to plot out a graph of its temperature. So what is this axis, the horizontal axis going to be?
Temperature.
What's the vertical axis?
Height.
Do you agree that the box should cool at 10 degrees Celsius per kilometer, which is called the dry adiabatic lapse rate? So I'm saying that we're going down, that this so-called slope, and it's not really slope, but it's ish, is going down 10 degrees Celsius for every 1 kilometer I go up, right? That's what the lapse rate means. So if I were to plot out the temperature of the average troposphere, what would that line look like if I start out the same? Where would that line be? Would it be like this, or would it be like this? First or second?
It'd be first.
First.
Right? Wouldn't it be the first one? Because it's at a smaller lapse rate. We said that yesterday, that the more this line is that way, the greater the lapse rate. This is smaller. That's, what's this lapse rate?
None.
None lapse rate, 0 degrees Celsius per kilometer. What's this lapse rate?
Negative.
It's a negative lapse rate. What's another name for a negative lapse rate?
Inversion.
An inversion. Okay, so skip that for a second. So there it is. So what I'm saying is I'm lifting the parcel up to this point, up to that point. And there's the temperature of the parcel right there. There's the temperature of the parcel at this height. Everybody, pretend that you took the box and lift it up there. Okay, so lift the box up to that point. No, because Lena, you don't have to move it this way. You're moving it just straight up. That's just the temperature. What's the only thing that you really should have done when you lift the box? What should it have gotten? Should be getting larger, right? Okay, so now you lift it up to that blue line, some height. Let go of it. What happens to it?
It fell and got smaller on the way down.
Why do you say it comes down? You say it fell down.
Well, I assume it is affected by gravity if I had to lift it up there.
It is affected by gravity. Would you agree that, I mean, without getting into a lot of details, we all suggest that gravity points downward? But that's not the reason it falls down. And the reason for that is, here's something that you just need to know for now. Air wants to move from high to low pressure. So which way does this box want to move? Which way is there lower pressure? Generally speaking.
Surface.
Right? The lower pressure should be up there. Surface is going to be the highest pressure. So this box, any box that I draw on here, wants to go down because of gravity, but it wants to go up because of what? It wants to go toward low pressure. What do you call the difference in pressure over a distance? Like, write down a symbol for the change in pressure over a distance in this drawing. What do you have?
Are you describing a pressure gradient?
Am I describing a pressure gradient? The answer is yes. So how would I write pressure gradient? Do you agree? A gradient is a change in something over a distance. This is a change in pressure as you go up. So how would I write that?
D P D Z.
I like using D, dP dZ.
That's a question.
That's a question.
I like that because it just makes you smarter that you're looking at calculus like, oh, that's just a pressure gradient. That's how does pressure change as you go higher, right? That's what that is. And if you practice, you'd get that. So there's an upward force. Now, to make this a force, I actually need mass, but I don't use mass. I use this density. So I have a balance. It looks like this, and you don't need to worry about it too much. Not at this point. I have a balance between this and that. And what do you call this first box? That's a pressure gradient force. Oops, actually, it's a vertical pressure gradient force, and this is gravity. Which way does the vertical pressure gradient force point? Up. It points toward low pressure. Pressure gradient force points toward low pressure. That's why air wants to move there. Which way does gravity point? Down. So there's a balance of two forces that are true in the vertical. Okay, so over here, and by the way, we call this balance hydrostatic. It's a hydrostatic balance.
Why hydro? Doesn't have anything to do with water, does it?
Maybe because, well, what it is we often use hydrostatic in any fluids discussion. And so that the term may have come from the study of water first, and then it just kind of stuck. And it's stasis. What does stasis mean, by the way? Something that's static.
Doesn't change.
It doesn't change, it's sort of there. So the idea is that this force is really balanced. So for this box, okay, now does everybody have a question on this? Okay, watch this. This is kind of interesting. For this box, we'll use this. There is an upward force for the box. And there's a downward force for the box. This is gravity. And this is the weight. Well, sorry. That's really not what I meant. This is gravity, and this is the pressure gradient force. PGF, can I do that? And it's balanced. Because there's a pressure gradient. Because at this blue line, what is the pressure? It's the weight of the air above you. So above the blue line, there's that much air above me. But what about over here at this box? Do you agree that there is still an upward pressure gradient that exists? And there's still gravity that exists going down. Do you agree gravity is the same because you're at the same place? But is the upward pressure gradient force the same? How many people says, okay, so what I really want to do is I want to go this. It's either this way, or this way. Which one is it? How many people say the gray is greater than the rust? How many people say it's less than the rust? How many people say it's equal? So give me left is greater than right, left is less than right, or equal. Okay. I have a couple people with different answers. Some people are pointing up, some people down. Did somebody do this? I think somebody did that. Which one is it? What? Tom, you were pretty quick to say it's down. Why?
Because the temperature is higher, meaning there's more pressure or the temperature is higher in the orangish one, so there's more pressure because there's more kinetic energy.
Close.
Oh, wait.
Somebody else? What do you think, Tim?
Well, I know that if your temperature is higher, that means the density is less, right? At the same pressure.
Oh, did you hear what he said? Okay, watch this. What is the pressure gradient force in grade? It's 1 over rho. Don't worry about the negative. The negative means nothing. I'm just being consistent with my life. dP dz. And what's the other one? 1 over rho, negative, dP dz. What's the same in both the left, the gray, and the rust?
Pressure.
The pressure gradient.
Yeah.
Both of those are the same. And so what I really should do is go, this is the same as that. But what's different? Which density is bigger? This side or this side? Who has a bigger density? Left side, because it's colder. Do you agree that cold air is more dense than warm air? Cold air is more dense, inversely proportional, when what's?
Temperature. Yeah. Oh, and pressure.
When the pressure is the same. Do you agree the pressure is the same at both points? So in this case, the density is bigger. That's bigger than that. But what does that make the left side force? If the denominator is bigger, what does that mean for that whole thing?
It's gonna be less than the right side.
Smaller. So this force is less. Less than what? Well, less than gravity. So what will this box want to do? Move down.
Move down.
This box will sink. The box will sink because it's more dense. More dense than what? More dense than the environment. Look at this diagram. Look at this whole page. Scale of 1 to 5. How well do you understand what you've written, what's written on this page? Give me a number. Okay, I've got a couple of 2s, 4. Tom's 4.5, I think.
Yeah.
3s. What's Aaron's at?
3.
3. Okay, those of you who are maybe at 2 or 3, you want to ask me a question? What do you want to go over again? What's confusing you? And don't say everything, because that's not true, but you can say anything. I'm looking at you guys, right? You're staring at this.
Oh, okay. Why is that one on the left more dense than the one on the right?
Okay, Nick, let's look at this for a second. I'll use a different color. What I'm saying is that what's in this box is being compared to what's in that box. Okay? in the circle is the same in both boxes. In this circle is the same in both boxes because that pressure gradient is basically saying how much is the pressure changing above it. Okay?
Okay.
So then the only thing that's left to be different is in this little red circle, is the density. So you have to ask yourself, what's more dense? This guy, the yellow box, or the air around it? Which is more dense?
Okay.
Well, cold air is more dense than warm air at the same pressure. So we say, oh, the gray density is bigger. But where is it located? It's in the denominator. If you make the denominator bigger, what does that make for the full square? If the denominator is bigger, that full square is smaller. And that's the mathematics that you have to kind of get in your mind. Does that make sense, Nick?
It makes a little bit more sense. Yeah.
So because the denominator is made bigger, the whole value of these things multiplied together is smaller.
Okay.
So if the green box is smaller, what is it? What is the pressure gradient force trying to balance? It's trying to balance gravity. But this upward force is smaller, which means gravity wins and pulls it down. So because it's colder, it's more dense, and then the air is going to sink. Did that clear up a little bit for some of you? Does that help a little bit? Any other question before I erase this? This is the time to ask. Let me do it. Let me do it this way because I'm just going to erase it like a whiteboard in class. I need to get rid of all this stuff. Hey, that was pretty good. I got rid of what I needed to. Okay, this is the parcel. Do you agree that the parcel is living on this little line? Because the parcel is cooling at the dry adiabatic lapse rate. What if the environment did this? What if the environment did this? When I lift the parcel to here, so go ahead, lift the parcel to there. It got a little larger, and then let go of it. Now what happens to it? What will happen to the parcel when I let it go with this environment?
Gonna keep going up.
It'll keep rising. Do you agree that the parcel is warmer than the air around it? Say yes or no. The parcel is warmer than the air around it.
Yes.
If it's warmer, the density should be less of the parcel, which makes this value bigger. So this upward force is bigger than gravity. So what will the parcel start to do?
Rise.
It'll rise. It'll rise by itself. When it rises by itself, it's because we say it is buoyant. That's what it is. It's because it's less dense than the air around it. So I lift the parcel, in that case, let go of it, and it rises by itself. What's the only thing that changed?
A core.
Between the first drawing and the second drawing.
In the environment.
The lapse rate, right?
the lapse rate of the environment, right? So the first one, the lapse rate of the environment was less than the dry adiabatic lapse rate. So I lifted the air and it comes back down. We say that's stable. On the second one, in this case, the environment is cooling more than 10 degrees Celsius per kilometer, and we call that unstable. Or what we call buoyant. So unstable and buoyant, as far as you're concerned, are the same thing right now. Does that make sense?
Right.
Say, I'm sorry, Tim, what'd you say?
Oh, this is like this happens always whenever the environment has a higher lapse rate than the dry lapse rate. It can float
So
up.
the greater the lapse rate, the more unstable, or the more likely it's unstable, perhaps is better said. But does anybody have something that they may guess ahead of time is problematic? What's the one word that I really haven't defined in any of this? Of all the things on here, what's one word that I haven't defined? That's your phone, Tim?
It's connected to my laptop somehow. I've got a Mac.
I hate that phone ring. That's like my phone ring.
I was gonna guess density.
No, we've defined density.
Okay.
Gravity?
I haven't defined gravity, but do you know what gravity is? Like if I said, here's a rock, I let it go, it falls, you go, oh, it's gravity.
Yeah.
Okay.
Would it be temperature?
We know what temperature is.
Oh.
Hydrostatic balance.
Well, I defined that for you. It's the balance between the upward force, pressure gradient, gravity coming down. Have I ever defined this word? Dry. What is this lapse rate called? The dry adiabatic lapse rate. What do you mean by dry? Did I ever tell you what I meant by dry? So take a wild guess. What other kind of lapse rate might there be if there's a dry adiabatic lapse rate?
Wet.
Oh, maybe the wet adiabatic lapse rate. So what makes something dry and makes something wet? Well, in order to do that, in order to understand that, I need to know something about water vapor. I need to know about water vapor, which is all the second unit. So what I need to do is I need to take a stopgap and say, okay, I want to go into the really cool stuff now because it's when air rises by itself, we get precipitation. So this is where we're going. This is just the foundation. We've built the foundation. Maybe we even put up some walls, but we have a lot of other things to do before we go on. So how are we at this point? Now are we okay with all this?
Is this where the hydro comes in and hydrostatic balance?
No, I really, to be honest with you, that's always bothered me too. I don't know where certainly in fluids we have hydrostatic, but why in air? I don't know, it just is. I don't know what the answer why that is. I think it's just that somebody studied water first and then we got air. But do we understand all this stuff? Okay, I need to go. I need to get out of class earlier. I have a meeting, so I need to be done by about 5 after 3. So I'm just going to continue going through that. We'll be done in about a half an hour or 35 minutes. Fair enough? You want me to just stop for 2 minutes if you want to do a quick bathroom or drink break?
Yeah.
Okay, why don't you just take 2 minutes, do what you need to do. All right, we're back. So this is hard stuff. This might be a good part of the lecture that you need to go through and try to get this again. This is hard, right? This is advanced level stuff. It's very collegiate. So when we go on, we're going to need to have this stuff done. You need to know this stuff really well, and you can't forget it. But there's a lot of other things I need to get done too. So I'm just going to pause this concept. We're not going to get into wet adiabatic lapse rates until the next unit. But right now we just have a lot to finish up and do some stuff. So this is going to be the easy stuff now. Does that make you happy? Here's the easy stuff. So I'm going to erase that, and I'm going to go to share the screen, and I'm going to go to, we got a lot of snow out there. It's not snowing anymore crazy hard. That was kind of fun for a while, but it's really wet snow right now at all. It's kind of half melted. I'm going to look at my class notes. So you have your class notes, Unit 1 notes. And now I'm going to try to go through this really fast because you guys are way smarter than this. I can draw on this. So the average height of the troposphere is around 10 to 11 kilometers, 15 at the equator, 5 to 6 kilometers. That's the tropopause, right? That's how high up the end of the troposphere. You need to star this and say, we're going to explain why is it thicker over the equator and thinner over the poles. There's a reason for that, which we'll get into. The troposphere is about 75% of the total mass of the atmosphere. So if the pressure on the ground is around 1,000 millibars, and when you're standing on the ground, how much air is above me?
100%.
75%.
All of it, 100%. When I'm at the tropopause, if I were standing at the tropopause or floating in space, how much air is still above me?
20 to 25?
20 to 25%. So what's the pressure at the tropopause?
Probably like 250, 200 millibars.
Between 200 and 250 millibars. That's it. And that's really up around, on the average, of maybe 10 or 11 kilometers above the ground. So that's all the troposphere. Now, this is where our weather occurs. We said the average cooling is 6.5. That changes all the time, as you saw, right? Some of the math lab assignments, I'd say plot these lapse rates, calculate the lapse rates. It's always different. This is just on average. Now, when we get to the next layer, the stratosphere, the temperature usually is fairly constant for a while, and then it increases. So your tropopause looks like this, and then it tends to go the same, and then it goes up again. And it contains about the rest of the gas. So when I'm at the end of the stratosphere, which is called the what? What's the end of the stratosphere called?
Stratopause.
Stratopause, right? How much air is above me? Not a lot. I'm usually at around a millibar. It's a lid to the troposphere. Aircraft flies in the lower part of the stratosphere. And then the question is, why does the temperature go up? Primary reason is that there is a gas that exists in the stratosphere that absorbs radiation. And that gas is called ozone. Ozone, and you need to know this right now, absorbs ultraviolet radiation. And ozone exists in the stratosphere, and that's why it gets warmer. Now, you get to the next layer, there's not much mass in there. There's hardly anything there. Temperatures get really, really cold at the mesopause. It goes to around 92 kilometers. Would you agree this is definitely the most dense layer? And this is, the mesosphere is a lot less dense by a lot than the troposphere. So most dense layer is the troposphere. Does that make sense? It's smallest, it has the most mass density. Then we go to this area where we start to get gases absorbing radiation, different types of radiation, but there's very few molecules. So here, take your hand, put your hand out in the air. Do you feel the temperature of the air? If I stuck my hand out the window, would you feel it? And the reason is you're conducting heat into the air. How many molecules are hitting your hand?
A lot.
A lot. Trillions and trillions of molecules are hitting your hand. So imagine that I was flying up in the thermosphere where it's really, really hot, and you put your hand out. Would your hand feel hot?
No.
Each molecule is hitting with high speed, but there's so few molecules, you wouldn't even feel hot. So you wouldn't feel hot. In fact, the first American to orbit the Earth orbited in the mesosphere. John Glenn orbited in the mesosphere. Thermosphere is like way up there. There's hardly anything there. When you have a shuttle coming back through re-entry and starts to burn up, it doesn't start burning up till somewhere in between these two layers, where the gas is actually dense enough to make a difference. Up here, it's like, it slows a little bit, but not much. Okay, so those are your 4 layers of the atmosphere. That is, how hard is that, right? That's not hard. Now you can call it the ionosphere. So high in the atmosphere, you have what's sometimes referred to as the ionosphere. The thermosphere is part of the ionosphere. What is an ion? Anybody know what a definition of an ion is?
Do with a charge, I'm pretty sure.
Huh? We call charged particle. So the molecules get charged, and because there's a charged particle, that allows electricity to flow.
Would lightning take place in the ionosphere?
Not lightning.
No. Okay.
That's a good question. What do you call it? Call it these things: the aurora borealis and the aurora australis. The auroras. So an aurora is when you see the northern lights, because that's what these stand for, the northern lights. What do you think this would mean? Aurora. Anybody from Aurora? Anybody? Or if can you imagine what the signs say? Welcome to Aurora, the
City of Lights.
City of Lights, because that's what Aurora means, lights. Borealis, a boreal wind. It's like Norse mythology, means the north. And then Australis, what do you think that is?
South.
South. So if I look at something like this, hold on a second. If I go to the Aurora Borealis, and I say, well, let's look at some pictures of the auroras, right? That's electricity flowing in the ionosphere. So you actually get plasma from the sun that moves across the ionosphere, and you get these disturbances, these electrical manifestations, so to speak. So that's what an aurora would be. That's what's going on in the high atmosphere. Where am I? Oh, there we go. So where else does electricity, who said that? Shannon? So where else do you see electricity flowing? That's where you get lightning. Now, do you agree that the air down here is not electrically charged? So for lightning to hit from the cloud, it needs to build down there. And really what happens is the lightning starts to do this, and it's very faint, you can barely see it. The lightning you better spell lightning correctly. There's no E. See, there's no E in lightning. I'll fail you if you spell it wrong. The lightning ionizes a path. to an object, the ground, for instance, a tree. Once that path is completely ionized, then lightning flies and it's really bright. So that's what lightning is all about. It's that electricity flow. So lightning and auroras are both electrical. And that's actually kind of important that you deal with this. Okay? And then we talk about, sometimes we call something the ozonosphere, the layer that contains the ozone, which is really in the stratosphere. And remember, ozone absorbs ultraviolet radiation. Fair enough? Now, there's a couple of other things, other ways of describing the atmosphere. One of them is called the homosphere. Homo is a prefix that means the same, as opposed to hetero, which means different. Okay. So what I'm saying is that in the lowest 80 kilometers of the atmosphere, the gases are all the same breakdown of gases. This chemical constituency of the atmosphere, 78% is nitrogen, 21% is oxygen. That's true in the lowest 80 kilometers. It's all kind of mixed up. Above that, the gases settle according to weight. So think about vinegar and oil, right? If you took salad dressing, vinegar and oil, and shook it up, it would all be mixed. But if you give it over time, the heaviest stuff sinks to the bottom and the oil comes to the top. So you layer it. The heaviest gases are on the bottom. The lightest gases are on the top. So when I talk about the weight of gases, what do I need to consider? What would I look at to determine the weight of a gas? Anybody know?
Density.
Composition.
Mass.
I would need to do this. Have you ever looked at this? The periodic chart of the elements. Have you heard of that term? Is everybody familiar with this?
Yes.
Okay. So the number, well, when I have a molecule, I guess we should start with this. When I have a molecule, what are the three parts of a molecule?
Proton, neutron,
Protons
and
and
electron.
neutrons.
We have the nucleus,
Yeah.
which is made out of what? What two things are in the nucleus?
Protons and neutrons.
Protons and neutrons. And then flying around the outside are the what?
Electrons.
Electrons. Electrons weigh something. They have mass, but very small. Most of it's the nucleus, or it's the protons and neutrons. They all weigh something. So each neutron or proton weighs one, basically. Okay? So hydrogen has an atomic number of 1, which means it has a proton, and then it has an electron, hydrogen. What's this guy here? Helium. You know what? I need to go to a different one. This doesn't have what I want. Can I use? No, that's crappy. I don't want to go to Amazon. Which is a good one. Give me a good. I'm not asking for something that difficult. I just want to see the image. There. There we go. No, that's not it.
If you just Google periodic table, the like first option is like a whole website of just like a periodic table.
This one?
Yeah.
Oh, that's fine. That works for me. Okay. So hydrogen has one, it weighs one, atomic number 1. Then we have helium. Now its atomic number is 4, which means it has 2 neutrons, 2 protons. Do you know this? Have you learned this in your life? I don't know what they teach you in high school anymore. So just nod your head if you've learned this, because I don't want to spend a lot of time on this. Okay, so we have hydrogen, we have helium. Oh, I like that. What's the number 1 most abundant gas in the atmosphere based on the notes?
Nitrogen.
Nitrogen. But nitrogen's chemical symbol is N2. And what that means is when I look at nitrogen, it has, the atomic number is 7, it weighs 14. So that's 7 neutrons, 7 protons. But we have it as a diatomic. That's what this 2 means. It's diatomic. That means nitrogen floating around in the atmosphere has 2 molecules connected. And it weighs how much? (14 times 2). So it weighs 28. What's the second most abundant gas?
Oxygen.
Oxygen.
But oxygen also is O2, and it weighs 15.99, or about 16. So nitrogen is 28, oxygen is 32. Do you agree that nitrogen and oxygen are really close to the same size? Okay, now we also have water vapor, H2O. How much does hydrogen weigh?
1.
It weighs 1, right? So there's 2 of them, that's 2. And then oxygen weighs 16. So how much does water weigh?
18.
18. Okay, that's how that works. Now there's another gas in the atmosphere that has 1% of the atmosphere. By the way, nitrogen makes up around 78%. Oxygen is 21%. What's the third most abundant gas?
Was it argon?
AR stands for argon, which is about 1%. Okay, now argon is interesting. Argon weighs 40. It's kind of heavy. But do you know anything about the gases that are over here in this column?
Are those the noble gases?
Noble gases.
Those gases are called noble gases. Helium, neon, argon, krypton, xenon, radon. What does it mean to be a noble gas? Noble gases are very non-reactive. They don't do anything. They're happy all by themselves. They don't want to react with anything. So helium has no problems. It's just helium. Neon, you can throw electricity through it and make lights, but it's a really noble gas. Argon is a very good noble gas. So you breathe in, take a big breath, and how much of your lungs were filled with oxygen? Oxygen.
21%.
About 21%, right? 20.9%, something like that. 78% of that is nitrogen. And nitrogen, when you breathe, all you do is exhale it. So the nitrogen goes in, it goes back out. You're not doing anything with it. Oxygen, what do you do with it?
Our body starts
It goes
processing.
into your blood.
What is it? You need it for your blood. It carries oxygen. You need this for energy. Oxygen is a huge cellular energy producer. And when you burn energy, you get byproducts. So what does oxygen get converted to?
Carbon dioxide.
Carbon dioxide. And what do you call the process of converting oxygen, getting energy, and converting it to CO2?
Respiration.
Respiration.
Right? You're breathing. That's what respiration is. So by respiration, you're taking oxygen, which gives you huge amounts of energy that you can use for your cells. And then you as a byproduct, it converts to CO2 and you exhale that. Now, plants, on the other hand, they like carbon dioxide and they convert it back into oxygen. What's that process called in a plant?
Photosynthesis.
Photosynthesis.
So plants are going to do that. So we're happy to be around plants because we respire and we respirate and they photosynthesize. Okay, but in your body, argon is an noble gas. It doesn't do anything. It's pretty boring. Do you know what we use argon for? There's actually a couple of things we can use argon for. How many of you have nice windows on your home? This is kind of an important thing. You have a window, and if you have, have you ever seen this? A thermal pane? They have a window, and you have two pieces of glass separated by something. So you will actually pump in argon into the window. So you have argon gas. Now why? Because if you break the window, what do you release? Argon gas. Does anybody get sick from argon gas? No. Do you agree that argon gas is also very heavy? So the density is good. Why put in air between two panes of glass? What's the reason to do that for your house?
Insulation.
Air is a good insulator. So your windows have insulation with argon gas. Now, do any of you have old houses? There's an old type of window that you have. It's one of those little metal ones you have to put your fingers in and like push them together and lift it up. Do you know what those are called? Lena, do you have those windows in your house?
No, I've used them before. I don't know if they're called they're a pain though.
Those are pane, a different spelling of the word pane. Those are called storm windows. Storm windows are not very good. A lot of air gets into them, so they're not very efficient. Thermal pane windows are really efficient. That argon gas keeps them really well insulated. So, I can touch my window right now. It's somewhat cool, but it's not that cold because the gas is much better at maintaining the heat. So that's what argon's used for. Now, what about nitrogen? What's nitrogen used for? It says in the notes. So if you go back to the notes, here's information that's already there for you. So nitrogen says we're going to break it down. N2 needs to be broken down into usable, actionable compounds. Those compounds of oxygen are NO2 or NO3, something along those lines. Maybe we would say NOx. And they're known as nitrites or nitrates. Whatever that means, right? Whatever those are. And then they're usable. So what's the usable form? What's the thing that eventually happens is we have to convert them into proteins. Proteins are all nitrogen-based proteins. The molecules are complex. Okay? And then proteins do a lot for us. Our whole body works on proteins. So is any of you, somebody pre-pharmacy here? Or is that my other class? Javi, what's your major?
Aviation.
Oh, aviation. Okay. Is anybody pre-biology something? Anything with bio? Okay. Okay, whatever. So what does that is what breaks down nitrogen into usable form? And the answer are bacteria on plant roots. And those plant roots, those plants are called legumes. Have you ever heard of legumes before?
Isn't a potato a legume?
Maybe. Here's the ones that are common: clover, alfalfa, and soybeans. And obviously, people who are like vegetarians often will eat soybeans because they have a lot of what in their diet? Proteins. So they are able to fix them. You know what else fixes them? Lightning. Lightning breaks down nitrogen. It acts as a fertilizer. So when you have rain falling, it's good for your lawn. When there's a lot of lightning, it releases kind of protein fertilizers for your ground. Then animals take this, they have waste, and they decompose when they die, and it goes back to nitrogen. That's known as the nitrogen cycle. Nitrogen cycle. And that's all I really want to talk about nitrogen. 78% of the air is nitrogen. It's, by the way, for those of you who want to know some cool stuff, if we didn't have nitrogen, things would blow up a lot. Nitrogen stabilizes our oxygen because oxygen, in addition to respiration, is also a main reason we have combustion. You take a candle in a jar, you cover the jar, what will the candle do?
Go out.
You burn up the oxygen, it goes out. Okay? It needs oxygen to burn. Now, there is something kind of cool that I want to show you. I think you'll like this. It's called a backdraft. And if I do backdrafts on that's a I do Tim in the backdraft. Let's see if I can. I'm looking for one that's really cool. Real life. This is the checkers game where grandson and granddad will bond. About halfway through the living room, me and my partner heard a boom, and then the ceiling fell.
A backdraft is caused from some type of combustible burn in the house and depletes the oxygen inside the structure. But because you've removed the oxygen, they can't burn. So once you introduce the oxygen back to it, it explodes out in a violent eruption.
So that's actually a pretty decent backdraft. I think this is another one that's kind of cool.
I want to show you this piece of video, this frightening backdraft explosion captured on camera in Ohio, and watch for the firefighters.
So what's going on, right? The fire's been burning inside. It could be, what do you call a fire that doesn't have enough oxygen? What does the fire do? What do you call a fire that doesn't have enough oxygen? Starts with an S.
Smolders.
Suffocates.
Smolders, right? That's what's smoldering. So when you have the fire, it starts to smolder. And you can have, like, hot logs can be a long time. They can smolder for a while. And then if you have a fire, what do you want to give it to make it flame up or to heaten up? Hot up, make it hotter. You blow on it, right? You have billows or you blow oxygen onto it. And then that will light the flame. So in a place, if sometimes you use up all the oxygen, it's still really hot and it's still smoldering. And then when they open the door or window breaks or whatever, that other house, a ceiling collapsed, then you get the explosion. So this is kind of cool. That's a cool big explosion.
Keep watching. You're going to see some of these guys coming out, crawling out. There he is. The backdraft caused all of the windows in the building to explode outward. It happens as 3 firefighters entered the building. Obviously, you see there, thank goodness they managed to get out unharmed. By the way, backdraft is caused when air is rapidly reintroduced to a fire, reignites it, causing an explosion. Here it is again.
So there it is. That's just a backdraft. So oxygen, respiration, and combustion. Those are the 2 things that are super important. And by the way, when you burn a fossil fuel, you're adding oxygen to it and fire or combustion of some sort. What's the byproduct? When your car runs, what are the 2 things it produces?
Exhaust.
Carbon monoxide.
Well, it may produce carbon monoxide. You don't want it to do that. That's dangerous. What's it supposed to produce? Carbon dioxide and water. Really important that you understand fossil fuels produce carbon dioxide and water. Okay? So just going through here, we have nitrogen, we have oxygen, we have argon. Remember, the word is inert, non-reactive, right? Do you know that word, inert? Carbon dioxide is used in photosynthesis, but the other thing that's super important is that it is known as a greenhouse gas. A greenhouse gas is any gas that absorbs infrared radiation, IR radiation. And this is what we're going to need to talk about. So on Monday, we are going to be doing greenhouse effect, global warming, and we're going to do all these other big parts in here. So what is due on Monday?
A reading assignment.
And what reading assignment do you have due? It's chapter 2. Okay, I am going to, listen to me, I'm going to change what's due on Monday. And I'm going to go do this online. I want chapter 2 and chapter 3 for Monday. Because there's no other lab. There's nothing else for you to do other than rewrite your notes, make sure you studied, and finish this up. This way you'll be a little bit ahead, okay? So this is going to be due on Monday also. We'll get you ahead. And then next week, we're going to talk about gases, greenhouse effect. Notice that we're almost done. So we're coming close to getting our tests. Not Monday, but Tuesday. So I tell you what I will do is this will be due Sunday night, and I'll give you till Monday midnight for this extra one. So I won't count anything late if you need an extra day to do it on Monday. Am I clear on everything, guys? Is that fair? That's fair, isn't it? This way it gets you a little bit ahead. And then after next week, we'll have the test sometime. Now, the way the tests are going to work is the test will work by, I will assign the test. I will give you a time frame where you have to take the test. I'll give you maybe 5 days. And there'll be a time limit on the test. So you have to find some time. I'm going to take the test, and then you're done with the test. You'll have plenty of time to do it. It's like 90 minutes to do the test. But that'll just be over a time period when you're ready for it, okay? Remember that the tests you have to work alone, but they are open note, which is why you're focusing on writing up a good class set of class notes. Okay? Tim, what's your major?
Ag business.
Ag business. You look like used to be a professor at CRD, Vic Gensini. Oh my God! Every time I see you, especially with the hat on, it's like.
Well, I'm about to shave, so.
I'm about to play. Oh, well, he's got this thing. So if you're going to lose that, then will I recognize you next week?
Oh, yeah, I'm pretty sure.
Okay. Anyway, guys, any questions before we end today? Oh, shoot. Don't leave. Don't leave. Hold on. I can stop recording.